This is NASA's Spitzer Space Telescope, which was a key tool in the study of planets around other stars, as well as the rest of the infrared universe. While only the size of an average car, it was a self-contained astronomical observatory that completed a 16-plus-year mission without repairs or resupply. Our simulated journey with Spitzer begins a few months after its launch in late 2003. You can see the calendar date of the simulation below the telescope. As we follow Spitzer in its orbit around the Sun, we will see the Sun drift across the background stars. Spitzer takes 8 more days to complete its solar orbit than Earth does. That means that it trails ever farther behind Earth, which in our sky appears as a bright blue dot. As Earth grows more distant over time, it will become fainter and appear to shift closer to the Sun. The visible light sky around us appears much as our eyes would see it, but Spitzer was designed to show us the wonders of the infrared universe. The dark ribbons of dust become ever more transparent, revealing vast populations of stars that fill our galaxy to its center and beyond. As we push into even longer wavelengths of infrared light, the clouds of dust themselves begin to glow, revealing intricate structures filling space between the stars. Many of the brightest areas are heated by the warmth of newly forming stars. But how was Spitzer able to observe the universe in infrared light? During Spitzer's initial cryogenic mission, its instruments were cooled down to a few degrees above absolute zero using a supply of liquid helium. At these low temperatures, its detectors were sensitive to the full range of the infrared spectrum, most of which is blocked by Earth's atmosphere. A shield covered with solar panels further protected the telescope from the Sun's heat while providing power. This constrained where Spitzer could point in the sky. If it tilted more than 10 degrees toward the Sun, then light would spill into the barrel, heating it up. If it tilted more than 30 degrees away from the Sun, it would lose critical power from the solar panels. But within those limits, it could pivot in any direction. This allowed observations anywhere in this 40-degree-wide swath of sky. As Spitzer orbited the Sun, this band swept around the sky, giving access to most locations twice a year. 2 regions, directly above and below us, were visible all year long. In this Earth-trailing orbit, Spitzer could collect data almost continuously, making it one of the most efficient observatories ever built. It only paused to aim its radio dish toward Earth for scheduled communication breaks. This is when it sent us its accumulated data and received new instructions, directing it to examine some of the most fascinating things in the universe. Spitzer helped astronomers determine the makeup of asteroids and comets in our solar system, map out regions of star birth throughout the Milky Way, detect planet-forming material around young stars, and study countless galaxies, including the most distant ones ever seen at the edge of the observable universe. Spitzer was also the first telescope to directly measure the light from hot, Jupiter-sized planets closely orbiting their stars. From this, astronomers determined global temperature and wind patterns, essentially providing exoplanetary weather reports. Spitzer's carefully managed supply of liquid helium lasted half a year longer than expected, but was depleted in May of 2009. Telescope temperatures increased to about 30 degrees above absolute zero. Still cold by most standards, but to astronomers, it marked the beginning of Spitzer's warm mission. While Spitzer could no longer see dust glowing at the longest wavelengths of infrared light, its studies of the universe continued in earnest. More remarkably, updated system software and procedures greatly improved Spitzer's precision, making it an even more powerful tool for studying exoplanets of all types, including smaller, rocky worlds. By 2016, communicating with the increasingly distant Earth required Spitzer to tilt increasingly toward the Sun, depriving it of solar power and putting ever more demand on its batteries. It was now literally operating beyond its design specifications in this final mission phase, appropriately dubbed Spitzer Beyond. The first observing program of this phase was a 3-week-long observation of an exoplanet system discovered by ground-based telescopes and thought to harbor at least 3 rocky worlds. The target was known as TRAPPIST-1, and Spitzer's nearly constant monitoring revolutionized our understanding of the system, revealing a total of 7 Earth-sized planets and helping to determine their physical properties. Spitzer continued its highly productive observations of exoplanets, stars, and galaxies until it was decommissioned on January 30th, 2020. With over 16 years of archived data that will support decades of ongoing scientific research, Spitzer has truly earned its place as one of NASA's great observatories.